All right, guys, we are reviewing how to graph a linear equation, linear function. So let's first recap what it means to be linear. Remember, every linear function is a straight line on a graph. They've got nice constant slope, and they have no weird stuff. Now that we've covered a little bit more of our different function types, we can kind of see all that different weird stuff. So if we look at this graph that I have over here on my calculator, right here, all these exponents are considered weird stuff. If I did the log of x, that's some weird stuff. I graph it. Look, that's not a straight line. If I do ln, that's called the natural log of x, and I graph it. Definitely not a straight line, right? Over here, what else is kind of weird? Oh, x to this weird -1 power. Looks like that. Crazy. Anything you just go, that's kind of weird. Sine of x. All that weird stuff, not linear. Slope. This is our rise over our run. It's the change in y over the change in x. We should be able to, on linear functions, count it. Now, every function has slope. The only thing that makes linear function special is that it's constant. It's the exact same slope all the way through a problem. So over here on my calculator, I graph an x. We have that nice up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1 slope. But if I make that an x squared, the slope between any 2 points, so right here, it might be down 1, right 1. But then it's down 1, right 1.5, down 1, right 1 1/3, blah, 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 until eventually right here at the bottom, if I were to put a line right there, it's perfectly flat. Then it goes positive. So the slope is constantly changing when it's not linear. And then the last thing, ordered pairs. Remember, these are our coordinate points. X before y. So there are 3 different forms that linear functions like to take. And the first one, our favorite, mx plus b. This is called slope-intercept form, and that's for a reason. M is your slope, while b is your y-intercept. 0, comma b. So that's your x value and your y value. That's how it gets its y-intercept name. Now, the thing about slope, that I want to make sure that we're abundantly clear and you hear it a bunch, it's just m. It's not m and the x, it's just m. But the slope is always connected to the x. So if we look into the future at this problem right here, and there's no x, doesn't mean there's no slope. It just means that the m took the x with it, and we'll deal with it when we get there. All right, let's graph a couple of these lines. Slope-intercept form. So we know that this is our y-intercept, 0, -2. Then our slope, 3 over 1. 1, 2, 3, right 1. 1, 2, 3, right 1. We can go the opposite direction as well. Then we graph our line. There it is. Moving on to the next one. Y-intercept, 0, 2. Our slope, 4 over 5. There is that one negative in front, so one number gets to be negative. This one tells us 1, 2, 3, 4. Change your y down 4. 1, 2, 3, 4, 5. If we had put the negative on the bottom, we could go 1, 2, 3, 4, 1, 2, 3, 4, 5, the opposite direction. We then connect these dots with a nice straight line. Not my best line there, but it looks like that. All right, our next one, down 1, because our y-intercept is 0, -1. Then our slope, it's tricky. There's no numbers in front of x, but remember your slope is always in front of the x. And that's how we get -1/1. So there's a lot of dots that we can plot for this one. And then connect them like we're waiting for our food at a restaurant and we're 4 years old connecting the dots. This middle one right here is known to a lot of math people as the parent function. This is where all linear forms start, very basic. Our y-intercept is 0. We start right in the center. Then we have the most basic of slopes, that 1/1. They call this one the parent function because every single one of the other lines that we've even drawn here today all start right here. So why does this green line not look like this pink line anymore? Well, we made it 3 times steeper. Why doesn't this green line go right through 0? Well, we told it to go down 2 from the start. Why doesn't this pink one and this purple one line up? Well, we made it have a negative slope that caused it to flip. Everything that's negative in this problem becomes positive in this problem. Everything that was positive in this problem becomes negative in this problem because that negative means opposite. Why is it lower on the graph? Because we told it, start 1 space lower. So every single one of these numbers is literally taking this graph right here and causing it to change. Why does it go up 2? Because of that. Why is it upside down? The negative. Why is it not a nice 1/1 slope? Because we want it to be a 4/5 slope. And that's just it. On this last one for our slope-intercept form, there is no x. That does not mean it has no slope. What this one actually is 0x plus 4. We have a 0 slope. So we go up 4, and then we have a perfectly flat line. And there it is. So that's a 0 slope. This line is called y is 4 because everywhere on this line, y has a value of 4. If we had an x equals, it would be perfectly vertical. That's why when we look at our quadratics tomorrow, our axis of symmetry has an x equals because our axis of symmetry is a perfectly vertical line. All right, now we jump down to the seldom seen, but still important to know, point slope form. So point slope form gets its name because it tells you that you have a slope, m, just like the slope up above, and it tells you a point. That point is x1, y1, but the thing to remember about it is that they are opposite signs. Up here, they're very clearly negative. Down here, they're clearly positive. So we want to take that negative point. So point slope form won't necessarily tell us the y-intercept. It's useful in case we have a line that the y-intercept is very, very large, but we still want to be able to graph it on this nice 6x6 graph that I give you guys. So we look at this one. Our point is -1, +2, with a nice slope of 3/1. This one does not illustrate the fact that the y-intercept is not visible on the graph. It's right there. But we still graph it all the same. The only difference is we started from that dot instead of our y-intercept. Try it again with this one. We've got a 2, -4 starting dot. So 2, -4 puts us right there with a nice 2/3 slope. So we go up 2, right 3, down 2, left 3. There's our line. I'm going to put a little star. That's where we started. If we look closely, that's not a perfect whole number. Because it's not a perfect whole number, it might be more of a challenge to graph it from slope-intercept form than it is point-slope form. All right, this one right here, -3, +5 for our starting dot. Then our slope, down 3, right 2. Down 3, right 2. Down 3, right 2. Connect the dots. Again, it looks like our y-intercept was not a pretty nice whole number. So graphing it from point-slope form saves us a little bit of effort of not having to figure out what it is. Okay, this one, +1, -4. With a -1/1 slope. We could have converted this one into slope-intercept form and been just fine. It looks like that. And then last but not least, -4, +3. Down 2, right 5. Down 2, right 5. 1, 2, 3, 4, 5, right at the edge. That was our starting dot. Pretty impressed with my straight line drawing abilities right there. For some of them, some of the other lines not so good. But that one was not bad. And that's it, point-slope form. Oh, I didn't put my starting dot for this one. Let's go back 1, -4. Put a little star right there. All right, the last one, very common form that linear functions like to take, was our standard form. So standard form, remember, tells us nothing. All it tells us is that we have a linear function. That's it. So standard form, ax plus by equals c. There's no slope given, no y-intercept, no points, no nothing. All right, so the way that we graphed this, or we've been graphing it, is by making a table of values, something that we could do with any function on the planet. We just plug numbers in and we see what we get out. We could plug in 0 for x, we could plug in 1 for x, we could plug 2 in for x, 3 in for x, 4, 5, 6. All we need is 2 dots, so we just have to pick 2. Starting with the easiest one, 2 times 0 plus 3y equals 12. That's 3y equals 12, so y is 4. So that gave us our y-intercept. We could then plug in 1 if we wanted to. We would do 2 to the 1, 2 times 1 plus 3y equals 12 and try to solve it. We might get a fraction, we might not. But the easiest thing we can do is we can also plug in 0 for y. that allows us to find our x-intercept. Now, assuming both of those dots are able to be plotted, all we need is that. We've got ourselves a graph. If I wanted to make my line a little bit cleaner, I can see that my slope is 4 over 6, and 4 over 6 is really just 2 over 3. So I'm going to put in that dot right there, that dot right there to let me line up my line a little bit better without a ruler. Looks like that. Let's try it again with our tiny table technique, is what I've been calling it this year. But remember, building any function with a table. Heck, right here, second table. This is literally what the graph does to graph any one of our equations. The problem is the TI-84s can't graph in standard form. That's why they're all written in y equals format. Well, either way, 0 goes in for x. We then just solve this equation real quick. We got negative 2y equals negative 8, so y is 4 again. That's neat. Then we plug 0 in for y because we can. So 4x equals negative 8, so x is negative 2. Puts us on the other side. Again, right here, I see that I have a 4 over 2 slope, so I can go 1, 2, 3, 4 over 2, or even simplify it to 2 over 1, get a few extra dots in there. That lets me graph this line just a little bit neater. All right, last one. Biggest thing when we're using the tiny table technique is just to make sure that we're not leaving out any negatives. Negative 3 times 0 minus 6y equals negative 18. So negative 6y equals negative 18. Y is 3. That dot goes there. 0 goes in for y, so I got negative 3x minus 6 times 0 equals negative 18. Negative 3x equals negative 18. X equals negative 6. We're way over here. All right, if we get a few extra points in there, I see it's up 3 over 6. So that's really up 1 over 2, 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 up 1 over 2. Line up the dots just a little bit nicer, and there is our line. Now the last one, we haven't directly practiced too much over the course of this year, but we should be able to take any one of these functions right here and convert it into slope-intercept form and graph it. Especially because if we try the tiny table with this one, our x-coordinate is at 8, which we can't fit on this graph. So one technique, if we want to still use the tiny tables, if we're like dead set on tiny tables and we try it, we come over here and we've got, all right, we got x, we got y, plug in 0 for x, we get negative 2 for y, plug in 0 for y, we end up with 8. Ah, dang it, that one can't be graphed. We could just straight up plug in 1 and see what happens. We could plug in 2 and see what happens. We could plug in 3 and we could see what happens. Any one of those could help us graph this line just as easily. But we're going to convert it because that's just as simple as just plugging in random numbers. So we take 2x's from both sides. We have a negative 2x, we have a positive 16. Then we divide everybody by a negative 8. And y is 1/4 x minus 2. So what that tells me is not only the y-intercept and the slope, but moreover, I would have to have plugged in 4 to get my next whole number. All of these would have been fractions. So when you can't do tiny table and we don't see that going through, converting could be just as easy. All right, next one. Again, tiny table. If we look at it real quick, our x value is going to be at -10, which we can't plot. So we might as well just convert real quick. I've got a -3x and I've got a -30. I divide everybody by 6. And I get -1/2 x minus 5. So that starts me here. Down 1, right 2. Up 1, left 2. Up 1, left 2. Up 1, left 2. The next reason why we want to be able to convert is you might not have plugged in a number that you were able to graph. For instance, by plugging in 1, we get a fraction. We can still plot that one. 2, we're still barely on the graph. 3, we're off the graph. And those are a lot of friendly numbers. I don't know how many people I know that would have plugged in a negative value when given a chance. Like over here, 0. Then we went 1, 2, 3, 4. And we might have run out of room, especially if I put this right here on 6 and had the slope going this way. All the positive x values don't even fit on this graph. So we want to be able to convert just as easily as we can build a table. This one, converting into slope-intercept form, is pretty easy. We're going to distribute. And in this case, we're going to add 10. Y equals 4x minus 2. So if you don't remember point slope form, or you can't plot that because this point that it's asking us to plot is 3, 10, which is way off the graph, we have to convert it or build a table, which I'm going to guess we don't want to do. All right, even if our slope is a fraction, we still have to distribute it. Remember, when we multiply fractions, we multiply the top and then divide by the bottom. So in this case, I'm going to take an intermediate step. So -2 times 6 is -12. Then that's going to get divided by 3. So y minus 7 equals -2 thirds x minus 4. From here, we're going to add 7 to both sides. Y is -2 thirds x plus 3. Oh, there's my phone. Let me get it to stop doing that. So we start up there, down 2, right 3, down 2, right 3, up 2, left 3. And there is our last line. Tomorrow in class, we're going to be reviewing how to graph our quadratics. And then on block day, we're going to put all of this together and practice graphing our linear inequalities. That's when we had to remember, do we do a dotted or a solid line? And which way do we shade? And that's graphing linear equations.